In this video, we are going to discuss the idea of the limit of a function, and we will informally define what that is very soon. But as a leading question, I want to ask, how does the function f of x equal to x squared minus 1 over x minus 1 behave near x equals 1? Notice that if we plug in x equals 1 into this function, we get a 0 into the denominator. So x equals 1 is not even in the domain of this function. Plugging in x equals 1 here gives us an undefined value, right? We cannot divide by 0. But can we determine possibly what that value is close to, or what values near it are close to, rather? Well, let's go ahead and take a look at this problem. And I want to note a few things. So note that y equal to x squared minus 1 over x minus 1 is equal to x plus 1 times x minus 1 all over x minus 1, which algebraically would be equal to x plus 1 if we canceled out x minus 1 over x minus 1, except at x equals 1, right? Because this expression x plus 1, or this function x plus 1, has a value at x equals 1, whereas this does not. So these two things are equivalent everywhere except at x equals 1. Well, let's draw those two graphs then. Let's draw the graphs of those two functions. X plus 1, y equal to x plus 1. It's easy to draw. That is here. And what about y is equal to x squared minus 1 over x minus 1? Well, as we've seen up here, these are the same functions except for at x equals 1. There is a hole in the graph there, but otherwise it is the same linear equation. So what we can see from this picture here is that x squared minus 1 over x minus 1, the value, the y value, tends towards 2 as x approaches 1. And that's the same thing over here. What does the y value approach as x approaches 1? Well, it approaches y equals 2. And what I like to do is draw a vertical line here, dotted vertical line, when we are talking about these limit problems at x equal to whatever value we're looking at, which we're looking at x equals 1 here. So draw this vertical line, x equals 1. And I really want to say, well, what does the y value approach as x approaches 1? Well, as we come in from this direction, again, we approach 2. And as we come in from the other direction, we approach 2. So, we say then that the limit as x approaches 1 of this function is 2, but I will write that out a little bit more formally in just a moment. So really what we're doing is, the idea of a limit is to ask what the function approaches as x approaches some value. And in this example, that was x approaches 1. All right. So let's give an informal definition of a limit here. So an informal definition of a limit. We'll have a more formal definition of a limit in a later video. But for right now, what I have written here is actually good enough for this class. But if we're ever going to prove any of the limit laws that we'll see later, we have to use a precise definition of a limit, which again will come in a later video. But for the scope of this class, what I have written here is good enough for the definition of a limit. All right, so suppose f of x is defined on an open interval about x naught, except possibly at x naught itself, then if f of x is arbitrarily close to L, what does that mean? That means that we can get it as close to L as we like for all for all x sufficiently close to x naught, i.e., again, let's read that again. If f of x is arbitrarily close to L for all x sufficiently close to x naught, then we say that f approaches the limit L as x approaches x naught, and we write this, which we read as the limit as x approaches x naught of the function f of x is equal to L. Which, if we go back up here, we would write this as the limit as x approached 1 of the function x squared minus 1 over x minus 1 was equal to 2. Similarly, the limit as x approaches 1 of just the function x plus 1 is also equal to 2. So both of those functions limited to 2 as x approached 1, i.e. the y value approached 2 as the x value approached 1. All right. Let's take a look at a few more pictures to kind of understand the idea of a limit graphically. And then that's how we'll end this video. So let's take a look at a picture like this. Let's suppose we have a piecewise function, and I'm not even going to write out what the actual function is. But suppose we have a function that looks like this. That's perhaps a piecewise function here. Doesn't even need to be a piecewise function, but just for this example, we have one. And let's suppose x equals 1, 2, maybe 3, 1, 2. So if we ask our question of what is the limit as x approaches 3 of this function f of x, right? So we just call that f of x. What is that? Well, what does our function approach? What does the y value approach as x approaches 3? Well, we see here from the picture that it approaches, the y value is 2 as we approach x from this side. And the y value goes to 2 here as well as x approaches 3 from the left. So for here, again, we have the limit is 2, i.e. the limit as x approaches 3 of x is 2. So again, this is just what is the y value approaching as x gets close to 3. All right. So we've seen an example or a couple of examples of when a limit might exist and what that limit is graphically. So I want to draw a few pictures, a few graphs of when a limit may not exist to give us an idea of what is happening here. So let's suppose we have a function that looks like this. So again, a piecewise function. And in particular, this piecewise function is f of x is equal to 1 if x is equal or less than 0, and it was, let's call this 2 if x is greater than 0. And so this would be a graph of this piecewise function. Well, what is the limit as x approaches 0 of this function f of x? Well, as we approach 0 from the right, we go to 2, and as we approach 0 from the left here, we go to 1. Those don't match. So what we say is that the limit does not exist, or we write DNE for that, for does not exist. Because again, what do we want? We want the y value to be close to 2 for all x near 0. And unfortunately, the y value when x is just below 0 here is 1, and it doesn't get anywhere close to 2 here. So the y value is not approaching 2 as x approaches 0 here, because we can see that from the left side. It is approaching 1 from the left. But does the whole function approach 1 on the right side? Well, no, that approaches 2, right? These y values are close to 2 up here. So again, it's just another way to say that this limit does not exist because the y value for all of the x values near x equals 0 do not approach the same value. They do not get close to a singular value. All right, so some more examples graphically. We have the function y is equal to 1 over x here. Then again, at x equals 0, the limit as x approaches 0 of 1 over x does not exist, because we don't have a singular value which the function is approaching at all points around x equals 0. Now, for clarification, if I ask for the limit as x approached any other value besides 0 here, the limit would exist. So if I asked for x equals 1, if we just plug this into the function here, this is the point 1, 1. If I asked us what the limit as x approached 1 of 1 over x is, well, we see that the y value approaches 1 here. So I'll just write that out. Limit as x approaches 1 of 1 over x is equal to 1. So that limit would exist. And that limit would exist for any x value that we approached other than 0 on this particular function, 1 over x. All right, I'm going to do one more picture here to finish out the video. Let's suppose we have the function f of x is equal to 0 if x is equal or less than 0, and sine of 1 over x if x is greater than 0. What does that graph look like? It looks a little crazy on the right side. On the left side, it's pretty easy. We just have this singular function y equal to 0 here, so this horizontal line. But on the right side, we actually get something that looks like this and bounces back and forth between 1 and negative 1. And it bounces all the way back and forth as we get closer and closer and closer to x equals 0. And it continually bounces back and forth forever. No matter how close we get to x equals 0, this is going to continually bounce back and forth between negative 1 and 1. So if we asked what the limit as x approached 0 was of this function f of x, defined by this piecewise function up here, well, this doesn't approach a singular y value because the y value is bouncing back and forth between negative 1 and positive 1 over here. So again, this limit does not exist. So we have a few examples where we can see, at least graphically, why a function may not have a limit at a specific point. And earlier in this video, we saw graphically how we could determine the limit of a function for some specific examples. In the next video, we'll move on to look at how to actually solve limits algebraically. So that's where we'll end this video.